What I thought I would do is to begin with a very brief review of, it has to be by necessarily brief review of the whole subject of climate change. I'm trying to boil it down to its essence. You can tell me afterwards whether you think I did a reasonably good job or not. And then transition to focus on the particular problem of how climate change might affect hurricane activity. Okay. So just to start off with some very elementary points, I'm just going to list the things that I think are kind of important about this, and skipping a whole bunch of physics and then a lot of history, but just to try to narrow things down. I would say that one of the most important first steps in this problem was taken by the Irish physicist John Tyndall in the 19th century, who did experiments. Remember, this is pre-quantum physics. They did experiments to show that amongst all the gases in the atmosphere, nitrogen and oxygen, which comprise the majority, basically are transparent to the passage of both solar and terrestrial radiation. There are very few absorption bands in those gases because they're very simple diatomic molecules, and that amongst the very tiny amount of trace gas left over, carbon dioxide is the most important long-lived greenhouse gas. Water vapor is actually more important quantitatively, but its lifetime in the atmosphere is 2 weeks or so. It's controlled mostly by temperature, so we consider it a feedback. This whole program of measurements that led Tyndall to these ideas were confirmed later by modern physics. Not very long after Tyndall, the Swedish chemist Svante Arrhenius, is how I think the Swedes would pronounce it, closer to that pronunciation anyway, estimated that doubling carbon dioxide, you see they were already worried about it more than 100 years ago, would cause an increase of about 4 degrees centigrade in the Earth's surface temperature. Actually had a higher estimate earlier, around 4 degrees. And you might compare that to contemporary estimates of this number, which we call the equilibrium climate sensitivity. It's just the response of surface temperature after it equilibrates to a doubling of CO2. It's just a definition. Modern estimates put it in 1.5 to 4.5 degrees C. So 100 and some odd years later, and countless millions of research dollars and experiments and computers and so forth, Svante's original estimate falls within the range of modern estimates, which I think is a pretty remarkable achievement on his part. Since about 1900, the concentration of carbon dioxide in our atmosphere has increased from about 290 parts per million to 400. And the global mean temperature has risen by about 0.8 of a degree C. And that, if you were to naively simply calculate a climate sensitivity from that, would give you about 1.6 degrees. But we might regard that as kind of almost an absolute lower bound in what we call the climate sensitivity for two reasons. One is we're not at equilibrium. We're far from equilibrium now. If we stop increasing CO2 and let it equilibrate, there will still be more warming before it equilibrates. And at least as important, there are other man-made influences that work in the opposite direction, mostly aerosols. And unfortunately, we don't quantitatively have very good estimates of the cooling produced by those aerosols. So that is almost certainly too low for an equilibrium sensitivity. During the same period of time, land temperatures have increased by about 1.25 degrees C. And again, if you were to naively calculate climate sensitivity based on that, you come up with 2.5 degrees. So the weight of, and I would say the weight of paleoclimate evidence suggests, and I will show you some of these things, suggests that carbon dioxide has played an important role in climate change on the time scale of millions of years and longer. It's I'll show you that evidence later on. We know that in the past few decades where we've been able to get reasonably accurate measurements of the ocean at depth, not just at the surface, the ocean heat content has risen steadily over this period of time. The acidity of the ocean is increasing. pH is decreasing simply because we're dissolving more and more carbon dioxide into it. This is not a climate change problem. It's just a direct chemical problem of dissolving more CO2 in water. Arctic sea ice and mountain glaciers are retreating. The upper stratosphere is cooling, which is a direct consequence of carbon dioxide, well predicted many decades ago. Sea level is rising. And so let me just go through some of this evidence. This is a chart showing the global mean surface temperature in green back to 1880, reasonably well measured, by the way. The blue curve here is proportional to the logarithm of carbon dioxide concentration. Theoretically, given where we are in the absorption bands, the radiative effect increases more with the log of CO2 than with the actual concentration. And you can see that Svante Arrhenius's prediction is relatively borne out by this. Okay, this is all very simple, once over lightly stuff. This is showing you the decadal average land surface temperature over this period of time, showing them the more like 1.25 degree increase we've had since the turn of the last century. As you go back in time, measurements become more and more sparse and the estimates become very uncertain, but for the last 100 years or so, they're fairly robust. The different curves are just estimates by different groups. The temperature change is not horizontally homogeneous. This is just the trend in temperature over the last roughly 100 years. And again, as predicted theoretically, it's larger over continents and larger at higher latitudes. Okay, there are even some places like the far North Atlantic and the southeastern US, which have seen a cooling over this period. Here is a reconstruction from various different paleoproxies of Arctic air temperature going back more like 2,000 years, showing a very slow decline until the beginning of the last century and an abrupt rise since then. And if we look on longer timescales, we can see how large a perturbation we really are making to the system. This is carbon dioxide concentration from ice cores going back to the last glacial maximum when the Earth was most recently at its lowest temperature. And as the Earth recovered from this, the carbon dioxide concentrations increased from about 180 to about 280 ppm, and that spike is what we've done to the carbon dioxide concentration. You can see it's a large perturbation, not only in the concentration of that gas, but in its radiative forcing. The lower chart is the same thing, but for another important greenhouse gas, methane. We've also greatly influenced the concentration of that. Now, on longer timescales, of course, the evidence becomes more and more tenuous as you go back. If we go all the way back 400 million years, this is a reconstruction of various quantities going back, including estimates of carbon dioxide concentration in parts per million here. As we'll see in a minute, these have huge error bars on them, but these blue downward bars here show various proxies for the presence of a lot of land ice on the planet. And you can see that during the two very long timescale periods when there was a lot of land ice were periods where the carbon dioxide concentration seems to have been low. If we blow up this last period, going back 60 million years or so, this is a proxy for temperature, really just deep ocean temperature. I'm not going to go into now what that proxy is based on. On the timescale of the last 50 million years ago, the Earth has been cooling, although not monotonically. And here are estimates with error bars, if you will, of partial pressure of CO2. And there's a general tendency for it to decline, but you can see that our estimates of this going back that far in the past are very sketchy indeed. Okay, so this is not by any means airtight evidence, but there's at least the suggestion that there is a regulation or a modification of climate associated with CO2 change. Now, one does not need big supercomputer models to do the basic calculations, as Arrhenius himself proved. Here is a calculation that you can do a few minutes on your laptop with a climate model, if you want to call it that. It's a one-dimensional representation of climate that really only includes transfer of energy by radiation and convection. Doing the canonical experiment of doubling CO2, here's the surface temperature. Versus that, you might consider this to be like a global mean. And if you just fit a straight line from a limited number of experiments, you get about 3 degrees per doubling, right in the middle of the range estimated in the most recent report of the Intergovernmental Panel on Climate Change, 1.5 to 4.5 degrees. So there's little doubt that you get an effect by doubling CO2, but there is a lot of uncertainty in the magnitude of that. Now, as to measurements, Here is a measure of the heat content of the upper 2,000 meters of the ocean, roughly half of it, maybe a little bit more than half of it. Going back to 1960, before that, measurements at depth were very tenuous indeed. The red curve, which we've had only for the last decade or so, are measurements by large number of essentially small robotic submarines called Argo floats that measure the temperature below the surface, come back to the surface and radio that information via satellite. These have been a huge boon to the measurement of the ocean below the surface, and they show that over the period of record there's been a steady increase in the heat content in the ocean. That, by the way, is something most people don't understand, is almost all of the excess energy that's created by excess greenhouse gas goes to heating the ocean, roughly 90% of it, and only a relatively small residual goes to heating the atmosphere. It doesn't take a lot of heat exchange between the ocean and the atmosphere to cause huge changes in atmospheric temperature. This happens naturally during El Nino, for example. And so when we talk about climate change scientifically, it's a little bit better to look at this ocean heat content than surface temperature, because of this, the fact that this is the main reservoir of heat on these timescales. This is simply showing the decrease in the pH of seawater near the surface. This is a trend over a few decades, showing that it is essentially decreasing everywhere. The ocean is becoming more acidic owing to the increase in dissolved CO2 content. This is feared to have possibly important consequences for marine ecosystems. Arctic sea ice, shown here in black in observations, has been decreasing. The red and blue curves are estimates from global models of what that sea ice should be doing. In this particular case, the rate of disappearance of summertime Arctic sea ice has exceeded even the envelope of what we thought might be likely based upon admittedly crude models of the process. This is just the mass of glacial ice around. These are alpine glaciers, not Greenland ice sheet and so forth around the world. It rapidly lost mass in the period 1945 to 1965, during which the world was warming rapidly. Then there was a period where the Earth wasn't warming so rapidly from the 50s to the 80s, and this loss leveled off, and then more recently it's been accelerating again. This is just, again, a map, but this time from satellites, of temperature change in the lower troposphere from 1979 to 2012, when we've had this kind of satellite measurement. And this is the same, but for the top of the stratosphere, where very basic theory tells you that increasing carbon dioxide must lead to a decrease in temperature. If you're interested in why, come and talk to me. It's fairly easy physics. If this temperature increase were produced by other agents, such as increasing sunlight, or cosmic rays, or other exotica that have been proposed, the stratosphere would warm as well. So this is a fingerprint of carbon dioxide, and that's one of the reasons that gives us confidence that this temperature change, at least in part, is due to the increase in greenhouse gases in the atmosphere. Sea level has been going up. Modern measurements from satellites are quite accurate on this. Before that, we had to rely on tide gauges, and measurements and estimates were less accurate, but there's no question that it's going up. A lot of the rise over this period can be attributed simply to the thermal expansion of water, seawater, as it warms. Seawater isn't 100% incompressible. It does expand as it warms. So that's my climate change in a nutshell. And I want to say something by way of transition into the hurricane problem by saying that there are really, in some ways, this whole story is a story of two perspectives. And I think a lot of confusion and angst, and in some cases anger about this, come from a failure for us, including us scientists, to distinguish between two very valid perspectives that are valid in different realms. And I'm going to talk about those. The first is the science perspective, When we look for a signal in data and science, we are necessarily and correctly little c conservative about that. We place a very high bar on statistical significance. We don't want to say, and we shouldn't say, that a signal exists unless it's clearly emerging from the noise. All right? We have an appropriately skeptical view of both theory and measurements. They both have problems, as you know, if you've done any research at all in the laboratory or theoretically. But in spite of these, we have collectively a high level of confidence that the world is warming, and that it is warming principally in response to increased carbon dioxide. But we have a low level of confidence in the estimated equilibrium climate sensitivity, because of lots of problems both on the theoretical and on the measurement side. We have low confidence. We are uncertain about the sensitivity of climate to CO2. But now we have a second perspective, which is equally valid and important in a different realm, which is the risk perspective. And the risk perspective is quite different. It puts and must put far more weight on the damaging tail of climate change outcome. This would be true not just for climate change, but for anything. When we look at risk, okay, we're necessarily concerned about the tail of the risk. The illustration I like to use is if a little girl comes and asks you whether she can cross a busy street, and as a scientist you estimate the probability of her making it unscathed at 95%. Okay, so with 95% confidence, you've let her cross the street. Well, of course you don't think about it that way, but you look at the tail without being told to look at the tail. If it's 5% or 1% that she'll be killed, she doesn't cross the street. Okay, it's a different perspective, and we have to sort that out. So we put more weight on the tail. To be conservative in this realm is almost the opposite as to being conservative in the scientific realm. Conservative approach warrants insurance policies, if you want to think of that term broadly, weighted toward the dangerous tail. All right? This is what we all do when we buy insurance. You pay a lot more if you own a car for your car because of safety features like airbags that in all probability you will never need, I hope you never need, during the lifetime of the car, okay? We just look at it differently when we look at risk. And so climate change involves risks. I don't have time you've heard all about those risks. It's a problem amongst other things. It's not just a science problem, it's a problem in risk. And the bottom line here, and I think this is almost an absolutely true, so there's little scientific support, I would say no scientific support, for any claims that risk is zero or manageably small. Now, it's a risk problem. It doesn't mean that things won't turn out all right. It's just that the evidence we have in front of us now don't warrant any claim for zero risk. Okay, that's a different thing from saying that there's a PDF out there, the low tail of which isn't terribly risky. That's also a correct statement. All right. Sorry? PDF? Oh, probability density. Sorry. Thanks for catching me out on that. A probability density. Yes, okay. The other problem with the risk is the time scales involved. This is simply a chart showing what would happen to carbon dioxide if we keep burning it, keep burning carbon and releasing carbon dioxide in the atmosphere, and then suddenly absolutely quit emissions when the concentration reaches 450, 550. So if we pay attention to the rate of decay, there's an initial decay that takes decades, but then there's a longer decay that takes centuries to millennia. So you put that is because of the biogeochemistry of the carbon cycle, okay, and the rate at which it has to be absorbed principally by the ocean. It's a long, long time scale. And correspondingly, the global surface temperature response, it takes a long, long time. So one could quibble about the exact magnitude of these timescales, but the point is that unless we can engineer our way out into taking carbon actively out of the atmosphere, and that's not impossible, that we might be able to do that economically. If we can't do that, whatever decisions we make in the next few decades are basically going to determine the carbon content of the atmosphere for millennia. That makes the problem more difficult to deal with. All right, in that perspective, now we're going to switch over to hurricanes. That's because I work on hurricanes and am interested in them. It is one of the more potentially bad consequences of climate change. Probably not the worst by any means. I mean, people who study this problem think that perhaps the worst effect of climate change is its effect on the hydrological cycle. Very different distributions of rainfall and evaporation that one gets, leading to major shifts in agricultural production, leading to food and water problems in many parts of the world, leading to armed conflict. At least that is what our own Defense Department is worried about more than anything else. So in my mind, that's the major risk. And you go down the list, sea level rise, particularly if it accelerates, puts a lot of coastal cities at risk. But increased storminess is among the other consequences. But beside that, it's very interesting. You know, I find it a very interesting problem. And I was interested in it even before it got to be a big deal in the climate scene. Like, were there more or fewer hurricanes in the last ice age? I'd sort of like to know the answer to that problem. So don't lose track of the fact that it's kind of an interesting problem in it, fundamentally. So let's talk about that. Some very basic theory, and this again is once over lightly. This is a cross-section through an idealized hurricane. Think of it as circularly symmetric and steady in time. They can be very nearly both for a while. So here's the central axis. Here's the eye wall cloud, and a hurricane can be described as a relatively elegant and simple example of a Carnot heat engine, where the heat is supplied from the ocean when water evaporates into air flowing in toward the center of the storm. And that heat is ejected at the much lower temperatures that one finds high up in the atmosphere. In fact, if you follow air around the circuit, it turns out to be, in almost a spooky way, an exact analog of what Carnot himself envisioned as the most efficient possible heat engine operating between two fixed temperatures. You have isothermal expansion as air moves toward lower pressure and acquires heat from the ocean, adiabatic expansion, and then isothermal compression in the lower stratosphere and upper troposphere at a much lower temperature, another adiabatic leg. Now, some of you might be thinking, well, how can I describe this leg as adiabatic when all this latent heat is being released when water condenses? That's an internal transformation. It is not an energy source, and textbooks get this almost uniformly wrong, okay? All you have to do is simply define the entropy to be the entropy of a combination of dry air, water vapor, and condensed water, all of which to a good approximation are in thermodynamic equilibrium. So the heat source is the ocean. It's evaporation from the ocean. It happens because in radiative convective equilibrium, the atmosphere is not in thermodynamic equilibrium with the ocean. It's in fact greenhouse gases that force it to be out of equilibrium. That provides the potential for hurricanes, and it's also why hurricanes begin to die as soon as they move over land, okay? It's very elementary stuff. Now, I'm not going to belabor the point, and I think I have one equation in this talk, but it is MIT, so I should be able to get away with this. This is an equation for the square of the maximum wind speed. We call that the potential wind speed, or potential intensity. And it's proportional to some non-dimensional coefficients. The temperature difference between the sea surface and the outflow layer of the hurricane, T0. And then this is the driver. It's the difference between enthalpy of air saturated at seawater temperature and the actual enthalpy of air in the boundary layer. This equilibrium is made possible by the greenhouse effect. We can calculate these quantities easily from climatological data and make maps of the annual maximum potential intensity in the current climate, shown here in meters per second. This is from a purely thermodynamic argument. And when we look at real storms, we see that this is in fact a very good way to normalize actual hurricanes. Most hurricanes don't achieve this potential intensity, but if we normalize observed intensities by potential intensities, the histograms of hurricane occurrence collapse to universal functions, I should say two, it turns out. One for storms that fail to achieve nominal hurricane strength. I used to think that was an arbitrary transition. And one for storms that do achieve hurricane strength. So this is the actual lifetime peak wind speed divided by the potential wind speed, and this is simply the cumulative frequency, so the number of events that exceed the value you see on the x-axis. And there are straight lines, so they're very interesting, very simple distribution functions, but they're two different slopes depending on the stage of development of the storm. And if you don't normalize by potential intensity, you don't get these two universal curves. So that's some indication that they play a role. That quantity, in fact, is important for real storms. Oh, I said there'd be one. I lied. Sorry, I forgot. What determines this disequilibrium at the sea surface? Well, in energy equilibrium, there is an equivalence between a turbulent flux of enthalpy, which is modeled usually as proportional to this difference, same difference that drives hurricanes, times the mean wind speed, like the trade winds of the tropics, times some coefficients. That has to equal the net flux of energy by other means through the ocean. So this is simply the net radiative flux into the ocean, the net downward flux into the ocean. And this is any convergence of heat by ocean currents that occurs. So that, in a long-term mean, dictates what this thermodynamic disequilibrium is. If we combine that with the expression for potential intensity, which involves this, we get a long-term, if you will, climate expression for it, which has on its right-hand side this same kind of thermodynamic efficiency that depends on temperatures. But over here, it has the net radiative flux plus the ocean heat flux, and then the mean wind speed occurs down here. So one way to increase potential intensity is to increase the net downward radiative flux in the sea, which you can do by increasing greenhouse gases, or by increasing the convergence of the flux of heat by the ocean into the column, or by decreasing the mean wind speed near the surface that you find in the tropics. So those are all ways you can do that. It is often stated incorrectly in the literature that the sea surface temperature is what dictates the wind speed in hurricanes. That's just plain wrong. But sea surface temperature, except there's a weak dependence here, it's very, very weak. The sea surface temperature is a cofactor. It varies with some of the same things that the potential intensity depend on. But in no sense does it cause hurricanes to be the intensities they are. The other thing that's important to note is that this downward flux has an upper bound. If you keep increasing greenhouse gases, this does not increase indefinitely. It asymptotes to the solar constant. So essentially you have the solar flux into the ocean and no infrared flux. If you have too much greenhouse gas in the atmosphere, there's no net IR flux at the surface. So this is bounded from above, and you can see that in experiments, again, with a single column model, showing this potential maximum wind speed as a function of the number of CO2 doublings in the system. At first it goes up, but by the time you're up here, you're almost saturated in the infrared because there's so much CO2 and water in the atmosphere. It's hard to get the potential intensity to go above this limit, except by changing something else like sunlight or the mean surface wind speed in the tropics. On the other hand, if you look at climate models, here is one result from a climate model at Princeton, New Jersey, the GFDL laboratory there, looking at trends in potential intensity for one of their simulations with a rather high level of emissions of carbon dioxide over the coming century. So this is really a trend over 100 years, showing the change in potential hurricane wind speed in meters per second, contoured here. And you can see that in the deep tropics, where you're not very far from being saturated in the infrared, there are modest changes of a few meters per second. But in the peripheral zones, particularly in the northern hemisphere, the Mediterranean Sea, the subtropics of the Pacific and Atlantic Oceans, there are really quite remarkably big changes in potential intensity on the order of 10 to 20 meters per second per century. Okay. Now, if I showed you a different climate model, you'd see a different map, but the features I just emphasized are pretty much common between the climate models. The details differ. in actual data, if we calculate potential intensity from reanalysis data over the period 1980 to 2010, we do see some indications of increasing potential intensity in the tropical Atlantic and in the peripheral regions of the tropical Pacific. That is, again, as predicted by the models, sort of in the subtropics around 30 degrees latitude in both hemispheres. So there is some indication from reanalysis data, one can quarrel with how good that is, by the way, of increases in this wind speed limit, if you will, that we apply to hurricanes. Now, that isn't the only thing that governs the behavior of real hurricanes. If you were paying attention when I showed the cumulative distributions of normalized intensity, you realize that most hurricanes don't come up to this limit, just a small number did. Haiyan, for example, that occurred a little more than a year ago and devastated a large portion of the central Philippines, was very close to its theoretical limit. In fact, the devastating hurricanes are pretty close to that limit in general. But it isn't the only thing going on, and there is a thermodynamic inhibition to hurricanes, which we call chi. Actually, it's the inverse of chi, but it's the same thermal disequilibrium at the sea surface divided by a measure of how dry the middle troposphere is. The drier you make the atmosphere 2 or 3 kilometers above the ground, the more difficult it is to get a hurricane in the first place. And that's why we don't have hurricanes everywhere all the time. It's because there's this inhibition. If that inhibition increases, this parameter chi goes down. And if we look at the same climate model that I just showed, you can see this is now the trend in this chi parameter. It's negative almost everywhere. So that's weighing against the formation of hurricanes in the first place. We try to put the two together by developing an index empirically that involves both chi and potential intensity, and trying to fit it to known climate variability of hurricanes, like the seasonal cycle of hurricanes, and interannual variability and the spatial distribution. It depends on more than thermodynamics. It depends on wind shear in the atmosphere, a measure of the spin of air at low levels called the vorticity. And this is just curve fitting. That's all it is. It's nothing more than that. Curve fitting to the current climate, the seasonal cycle. We get this index. There are lots of different variations on this, as you might guess, since it's empirical. And it involves wind shear, potential intensity, this chi parameter, and so forth. And we can only look in simple models at the thermodynamic component of this. And when we do that, we find that in the tropics, it's this, the change in inhibition kind of cancels out the increase in potential intensity. You get almost no change at all. But in this peripheral region of the subtropics, the increase in potential intensity overwhelms this increase in inhibition, and you get increases in these regions here. That's for this particular model. Okay, enough about that. In fact, I think I'm going to skip over this. Now, we can also try to do the problem of hurricanes and climate by brute force. All right, this is the preferred approach in my profession. I'm trying to change that because I think theory is more interesting and perhaps more important than brute force. And by brute force, I mean just put it on a big computer and simulate the hell out of it and see what comes out, right? This is what everybody's doing. And I think it's led us into some very bad logical traps. And I won't belabor that here. I could spend the whole seminar on it. But I did want to get across the philosophical part that this whole problem has been not really tractable today to try to do this in a global model, but that's the way people have been doing it. It's one of the reasons that my colleague Dan Rothman, who's here, and I founded the Lorenz Center at MIT, is to try to foster in all realms of climate science a basic approach, going back to basics. Understand the problem. Don't just simulate, okay? We've done too much simulation and not enough understanding, and that's got us into trouble in the hurricane arena. To be a little bit technical about it, the eye wall of a hurricane, which is where a lot of the physics happens, it's the ring of heavy rain and wind surrounding the eye, is an example, actually, formally, of an atmospheric front, even though it's a circle rather than a curved arc or something. It has the dynamics of a front, and it has typical scales of a few kilometers. And we know from doing experiments with detailed numerical models that we have to have numerical meshes of a few kilometers to claim to be numerically converged when we try to simulate storms. In other words, we see big differences going from 5 kilometers to 1 kilometer grid meshing when we try to do that. So there's a steep numerical requirement for doing hurricanes. You got to have a computational lattice whose grid points are separated by no more than 1 or 2 kilometers horizontally so that your storm is well simulated, all right? But the storm circulation can extend easily out 1,000 kilometers or so. And if you want to simulate them on an Earth, then you're talking about, well, you know what the circumference of the Earth is, right? So global models, which are often used to tackle this problem today, typically have computational nodes that are 100 kilometers apart. And yet they try to use these models to simulate hurricanes and how they'll respond to climate. I think this is just plain crazy, but almost everybody I know in the problem is doing that, okay? It doesn't make a lot of sense. And so they do, of course. The models do try to produce facsimiles of hurricanes. But they cannot simulate, they do not simulate the high-intensity storms that we see in nature, which do a disproportionate amount of damage. So in the United States, over the last 100 years, 80% of the normalized damage, corrected to modern times, has been done by category 3 and 5, 3 to 5 hurricanes, which constitute 13% of the total, none of which can be simulated by a global climate model today, none of which. All right, so we have a big problem. And one solution to this is to embed a very simple hurricane model that's very importantly coupled to the ocean. Hurricanes have a strong effect on the ocean. They upwell or they stir up to the surface cold water, which tends to reduce their intensity, an effect that's not well simulated by current climate models. And so we have to do that. And we basically use the large-scale climate models to do what they are ostensibly good at, which is simulating large-scale climate, to drive these. The particular model I'm going to describe here is called, it was developed here at MIT, called the Coupled Hurricane Intensity Prediction, or CHIPS. It was developed in the 1990s as a laboratory tool for students in a course. And then we found out that we could use it to forecast the intensity of real hurricanes in real time. So today it's being used as an aid to forecasting intensity by hurricane forecasters. Its sort of key feature is something borrowed from fluid dynamics that was done commonly 50 years ago when computers were really slow, which is to discover that there are coordinate systems better than physical coordinates in which you phrase the partial differential equations that make them simpler and more effective. And in this case, the coordinate system we use for radius, instead of being physical radius, the independent variable is angular momentum away from the center of the storm. There are lots and lots of advantages. The partial differential equations lose a lot of their nonlinearity when you do this, and you get very high resolution in proportion to how intense the storm is. So as the storm gets more and more intense, in physical space, these coordinate surfaces get closer and closer together. So this is something that was done commonly in fluid dynamics 40, 50 years ago, but people don't bother doing it today for a lot of reasons. Mostly because computers are so much faster, but they still have a lot of advances. And as I mentioned, it's been used to make real-time forecasts of hurricane intensity. In fact, you go to this website here, you can get forecasts for current storms anywhere in the world. As it happens today, there aren't any storms anywhere in the world. That doesn't happen very often, but today is one of those days. This is an indication of how well this model works. So this is a measure of the performance of different guidance products for hurricanes this year in the North Atlantic. although officially the season isn't over yet, probably it is for practical reasons. This is simply the difference between the forecast peak wind speed in the storm and the actual peak wind speed that was later measured. The leftmost bar is a subjective forecast made by professional weather forecasters, somewhat subjectively. The next bar is the model I just described. And the bars over on the right are very high computationally intensive models that are run at various places to forecast hurricane intensity. So especially at the far ranges, this is lead time. This is 12-hour forecast, 24, 36, 48, 72. So of the actual deterministic models in these later lead times, it's this simple model that has some of the lowest errors. This dark red bar is the state-of-the-art model in which millions of dollars were poured and which you have to call the power company before you use it. The model I just described, the CHIPS model, can run on that laptop in about 15 seconds, all right? This is what I mean by, there's a point to thinking about the problem and not just mindlessly simulating stuff. I don't mean so much to belittle these models because they do a lot more than just forecast the intensity of storms. So can we use this to transition between science and risk assessment? Can we actually use this sort of science model to help us estimate hurricane risk in the present climate, but also in future climates? Now, why would we want to do it in the present climate? You could say, well, look, we have history, and all insurance companies, for example, when they estimate hurricane risk, simply look at the historical record. But the historical record's awfully short, and it's very deeply flawed. We never measured hurricanes and even today we don't measure hurricanes for the intent of creating a climate record. They're measured so that we can make the next forecast. And we'll use anything and everything we can to measure them, but we don't keep record of what we actually used. And so the hurricane database is really poor for climate studies. So can we use physics to get a better handle on this? So what we do with this model is kind of simple. We take the world's atmosphere and oceans as represented by a gridded climate data set or a model, and we randomly seed it with sort of incipient tropical cyclones. We track them because in a very simple way, these cyclones pretty much move with a large-scale atmospheric flow in which they're embedded, like a rotating cork in a stream, if you want to use a metaphor for that, an analog for it. And then we use this CHIPS model to estimate the evolution of the wind speeds in the storm. And when we do that, this model correctly predicts that about 98% of the seeds you put down just die a natural death because you put them in a place which isn't very favorable for them to form. And so you keep doing this and you regard the survivors as constituting the actual climatology. So we sort of borrowed that one from the biologists. It's kind of a natural selection algorithm, okay, that just picks out the winners from this whole mass of storms. But it's easy to produce data sets of 50 or 100,000 events this way with very little computational resource. So we use this small fraction of surviving events to determine the storm statistics. And then, of course, the real trick is you can dream up these things, but does it work? So we have to try in many, many different ways to compare them to reality, at least as represented in the historical archive. So here are for the Atlantic, for a particular data set, the points of the sea disturbances that turned out to survive, and the comparable points called genesis points from observations. Now you see some similarities and differences. For example, there's a region north of Venezuela in the Caribbean where there aren't very many events, and that's seen in both observations in this. But you see some real events up here. Here's a hurricane that supposedly formed right off of Long Island, and nobody who studied tropical meteorology would believe that for 1 second. They can move there, but they can't form there. So why is that there? Because the people who put together this database didn't distinguish correctly between a genuine tropical storm and a winter storm. So you have problems with the historical records all over the place. Same for these points up here. So This is just arbitrarily 1,000 tracks that have been produced from a climatological large-scale data set with the colors showing intensities. If you know something about hurricane tracks, it's sort of a very zero-order reality check, but not much more than that. It produces a nice intensity distribution. So these are the number of events whose peak wind speeds over their lifetime exceed the value on this axis. The blue is from historical data. The red is from this technique. The error bars show confidence limits if the historical data, which is only 211 tracks, were just subsets of the synthetic data, then 90% of them should fall within those green bars. Here's an interesting statistic. This is the rate of change of the storm's peak wind speed, and this is simply the log of the probability of encountering this rate of change, which can be negative as well as positive in these intervals. And since these are basically straight lines, we have shown that the intensification and decay rates of tropical cyclones are very nicely exponential in character. And there's no fat tail on this distribution. So for the meteorologists in this room, there is statistically no such thing as rapid intensification of tropical cyclones. Of course, you can always put a number and say if it's higher than that, we're going to call it that. But there's physically no distinction between storms that are rapidly intensifying and ones that aren't. This blue is from historical data. The red is from the synthetic data. The green are confidence limits. The storms do things that real storms do, like produce double eye walls sometimes. So this is the evolution of the peak wind in a particular event, and these green curves are secondary wind maxima that occur in rings outside the eye wall that contract inward. This, in fact, is the radius in this diagram at which these occur and replace the original eye wall. And in this case, there are 3 such replacement cycles for this particular rather intense artificial event. But because we can produce hundreds of thousands of these events, we can extend the analysis of risk to much longer periods. So this is an analysis of the so-called return period, which is just the inverse of the annual probability of events affecting the whole coast of New England. The green dots are what you get from historical data, the blue dots from this technique, and the red curve is just a theoretical extreme value curve fit to the blue dots, so never mind that for this. So with the green dots, you can get up to storms with return periods of decades, but you can take, with this technique, almost arbitrarily up to higher return periods. We just got finished doing an analysis for the Nuclear Regulatory Commission of hurricanes that might affect the nuclear generating station at Seabrook, New Hampshire, and they wanted the million-year storm. So we had to generate a lot of events for them. And it captures interannual variability. So this is a measure of storm power in the North Atlantic going back to 1980. The blue is from historical observations, which are flawed, and the red from this technique. And amazingly, we capture about 60% of the variance of the interannual thing. And these events can all produce rain. So this is accumulated rainfall along one of the hundreds of thousands of tracks we generated for New England, showing all kinds of topographic influences as well as dynamical influences. We use it to drive hydrodynamic surge models. If you remember Hurricane Sandy or Katrina, most of the damage done from some of these big storms is not from the wind, but from the surge, which is a tsunami-like phenomenon, but driven by high winds rather than earthquakes. But hydrodynamically, very much the same phenomenon. We use these specialized adaptive grids to do surge modeling. And we're able, and this was before Sandy affected New York, to estimate the probability of a 3-meter surge, which is what they experienced, as something like a 1 in 700 year event. So, and we published that well before Sandy. This is surge at the Battery in New York, where there's a tide station. So we have to conclude that we were witness to an extremely rare event in New York, or the climate has changed since the climatological data set we used to drive this model in some way. Okay, we don't, of course, can't distinguish between those two. But having done this, we can now take climate change into account, at least loosely, by, instead of downscaling climatological data, we downscale climate models. And I put up 6 for the 5 here for the people who are in the know in the room about what these mean, but these are climate models run by different places all around the world. And we're going to compare the historical period 1950 to 2005 to 2006 to 2100 under a rather high emission scenario. And this is green curve shows the model ensemble average predicted global number of tropical cyclones from 1950 to 2100. Today's climate, the global number is around 85 or so. It's predicted to go up by this method, but the green shading in the background shows the scatter amongst the 5 climate models. So not all models predict it to go up. Some predict it to go up faster than others. The red is this, if you remember from earlier in the talk, this Genesis potential index, which nicely predicts the ensemble mean. There's a pattern to this, so this is just the track density change over 100 years, showing a lot of the change in the western North Pacific Ocean, but also the North Atlantic, and a bit in the southern Indian Ocean as well. This is just the same thing, but for hurricane power. We can filter those tracks to be just those that affect a particular region. This is a study we did for the city of New Haven in Connecticut, where Yale is, showing the return periods in the current climate from a particular model in blue, and for a future scenario in red, showing that in all categories of intensity, the return periods in this case decrease, meaning that the high-intensity storms particularly become more frequent with time. It's even more true of heavy rain. This is storm total rainfall, current climate, future climate. This is for New Haven, Connecticut, so forth. So we have these tools, and they've been finally developed and tested against the current climate, but we feel a major limitation is the climate models that we use to drive them are all over the place, all right? Which is shown, for example, in this graph, again, published before Sandy, showing estimated storm surge risk in New York City in the current climate and in future climates. So this is just 4 different climate models, all of which, however, we added 1 meter to the sea level in estimating the surge due to projections of sea level rise under this scenario. And so the increased risk in the future climate is, a lot of it's due just to the fact that sea level goes up. So a given storm will produce a higher surge in the future climate. Now, when we look at 100,000 events, we see some weird ones, and I call them black swans. Dubai, okay, you've seen pictures like this. It's kind of a fantastic place. I've never been there. But you don't need to have a lot of imagination to see that it's very close to sea level, okay, right? The people who built Dubai didn't worry about hurricanes. Why? To our knowledge, there's never been a hurricane in the Persian Gulf. But our technique, when we run it globally every once in a blue moon, like once every 200 years, does produce an event in the Persian Gulf. Here's one that formed down here in the southern Gulf and moved along this track, and Dubai is about where my laser is here, hit Dubai on the 24th of August in this particular year. This is in the current climate. This is even the future climate, producing a surge of about 3.5 meters in that place, all right? So a very, very low probability event. But I think the people who designed Dubai might have liked to know that this is possible, right? Remember tail risk. Let me tell you with this last slide really what the crux of the problem is. That our current civilization, anthropologists will tell you rightly, is very highly tuned to the climate we've had over the last 7,000 years, which has been remarkably stable by geological standards, stable in sea level, stable in climate. All right? If you don't believe me, just think about all the major coastal cities, Boston, New York, Miami, your favorite coastal city. 20,000 years ago, which is nothing geologically, sea level was 400 feet lower, okay? those cities wouldn't be coastal cities, all right? It doesn't take a lot of sea level rise to really imperil those cities. So the question is not what's the ideal climate for human beings. It's an empty question. The answer is sort of obvious. It's this climate because we're adapted to it. You change the climate a little bit, you stress that adaptation. And in the field of hurricanes, this is very obvious when you look at hurricane damage. So what I'm showing you here is a plot made from taking very large sets of these hurricanes and passing them over a property value database, which includes a model for how hurricanes might damage that based on engineering estimates relating wind speed to damage. That's all it is. And this is a particular Japanese climate model. This is the probability density of damage in the range that you see in the scale here. This is a log, a base 10 log of damage in US dollars. So there's a million, there's a billion, and so forth. The blue curve is for the current climate. The green curve is for a future climate from this model. And they're pretty much identical, you think, looking at them. If you look very closely, you'll see there's actually a reduction of damage in the future in this sort of low part, or the main part of the distribution. That is, in this particular case, the model is actually producing fewer storms in a future climate. It's not impossible. In fact, a lot of models do that. But also, like a lot of models, at the high end in this tail here, it's actually producing more storms. So you see that little bit wiggle there, a slight increase in the probability of higher storms. So you say, so what? All right. Now we're going to show you exactly the same data, but displayed a different way. We're going to multiply the probability density of damage by the damage itself, such that when you integrate under the area of these curves, you get the total damage in a particular climate. So this next graph shows damage times probability density, again against log of damage. And now the areas under these curves show you the net damage from tropical cyclones. And you can see, if you look at eyeball the area, that it's gone up by more than a factor of 2, all right? So that tiny little tail, slight increase in the tail, produced a doubling of damage. Why should that happen? Because we're finally adapted to roughly the 100-year event. And that's a very important time scale of adaptation. It's several generations. We tend to be well built for events that occur about with that frequency. If you get a little bit over that frequency, things really start to go downhill quickly. And that's what's happened here. We have suddenly a lot more of the so-called 100-year events in the future climate. And of course, there will be an adaptation to that. And the whole problem is that the climate is changing on a time scale that's shorter than typical human adaptation time scales. If we were having this climate change over 10,000 years, nobody would be talking about this. We'd all slowly adapt to it. It's that we're outpacing our typical ability to adapt. This is what happened with Haiyan in the Philippines. No, it wasn't what happens to a developing country when it's hit by a bad typhoon. That was the US press. Very irresponsible message. The Philippines have Category 5 typhoons practically every year, and you don't read about them because they don't do any damage, because they're finally adapted to it. Haiyan was a little bit over what they ever experienced in the past, and that little bit killed a lot of people. Most of the people who were killed were in evacuation shelters that could take an ordinary Cat 5 storm. Just a little bit over the threshold, boom. Okay? That's the story. This is what we have to worry about. So, let me summarize. The weight of existing evidence supports the conclusion that unmitigated warming presents a significant risk, okay, to future generations. It's not a certainty. No risk is a certainty, all right? It's a significant risk. The scientific uncertainty about the nature and magnitude of the changes entails a low, but not tiny, risk of catastrophic outcomes, okay? So I'm not being an alarmist here. It's the uncertainty that worries us. If we were certain we'd be in the middle of the range of outcomes, maybe we wouldn't have to worry about this problem so much. We could just adapt. It's the tail that arises from our scientific uncertainty that has us worried, because we can't rule it out. It's a low probability, but it's not as low as the 1% probability of the girl getting run over by a car. It's not even that low, so we have to worry about it. Among many risks that are posed by it are extreme events, including hurricanes, which I happen to focus on here. It's by no means the worst of the things that might occur. There's a pretty strong consensus among the people who study these things that the frequency of high category events should rise, although there's a lot of disagreement about what will happen to low category events. But the damage is done by the high category events, and that will produce a greater number of storms that exceed empirical tolerance levels that have been arrived at by adaptation to the current climate. There's also a strong consensus that rain from tropical cyclones and associated flood hazards will increase. I didn't talk about this very much, but in storms like Mitch in 1998 in Central America killed 12,000 people, all from freshwater flooding produced by rain. And increased high category events, when you couple them with sea level rise, indicate a strong risk of increased storm surge hazard. So I've tried to mix a little bit of the general and the particular here, but I hope that worked for you. Maybe it didn't, but I'm happy to answer questions one way or the other.
Excellent. Let's have some questions, please.
First, just to be clear, a high category event is an event of great intensity?
Yes.
Okay.
Yeah, like I'm thinking of Saffir-Simpson categories, like you hear on the news. Yeah.
In an earlier slide, you had the CHIPS, was it the CHIPS model
Yeah.
that has been successful or had a low rate of lack of success, but it looked like the one that you described as the sort of professional forecaster was even better? Is that
Yes, that's commonly true.
Can
Yeah.
you talk about that a little?
Sure.
And the other
Yeah.
question is, the maps of the hurricane that sort of sweep across from the coast of Africa and then become more and more frequent, or more of them in the Caribbean basin, more or less. For the non-specialist, what's going on there? Does that have to do with the trade winds or something like that?
Well, I'm just going to answer the first part, in fairness to other people who have other questions. So the very interesting thing, there is something called expert elicitation, which has been studied for a long time. In almost all forecasting problems, a human being can beat a multiplicity of objective guidance by doing very little more than averaging it. Okay, this is something that's been noticed in the weather forecasting realm for many, many decades, is that the average of many different estimates of something is usually better than any one estimate. And so one of the things the forecasters are doing is they're not literally, but in some real sense, averaging over the different guidance they have available to them and coming out. Now, there is another problem which is not objective, which is that it is a travesty of our profession that I've been trying without success to correct for a long time, that the same folks who are making the forecasts are also evaluating the forecasts. And there's subjectivity in the evaluation. Is a hurricane 65 knots or 60 knots? You can't make that difference. And so this would be intolerable in any other profession. That's why we do double-blind stuff, but we won't do it in mine. And so there's a bias that the verification looks like the forecast, and that makes the official forecast look better. I don't know how to quantify that, on the other hand.
I read recently about the storm, the hurricane of '38, that it traveled up the East Coast extremely quickly.
Yes.
And
yes.
your statement that the hurricanes stir up the ocean and bring the cooler water, thereby lessening the effect of the storm, suggests that it's the fast-moving ones that become strongest?
That's a very good observation, and that is true by and large. That's very slow. I think I would put it slightly differently. Very slow-moving hurricanes usually become weak because of upwelling of cold water. New England is an interesting example, because once a hurricane leaves the north wall of the Gulf Stream, roughly the latitude of Cape Hatteras, it's thermodynamically finished. Okay, you cannot drive a hurricane over the cold waters between the Gulf Stream and New England. So they're all dying. They're all dying. Okay, but if they're moving very quickly, they don't have much time to die, if you will, to spin down, and their interactions with non-tropical weather systems, as happened very prominently in the case of the 1938 hurricane, can actually even lead to a brief intensification of the storm. That didn't quite happen in New England, but case of the New England hurricane, but still very strong when it got here. It also has practical ramifications, like in New England, you can almost bet that all the strong winds will come from the south, because the storm, very crudely speaking, the storm translation is added to the circular winds, so it's on the right side where you have southerly winds, you're going to get the strong winds. So I keep telling insurance companies, those poor people on the north shore of Cape Cod shouldn't be paying the same rates as people on the south shore of Cape Cod, but they won't listen to me.
More questions, Nick?
I think I asked you this before. Why aren't there any in the plot you showed with all the spaghetti?
Yes,
Why
the
aren't there any
spaghetti.
the South
Yeah,
Pacific?
South Atlantic. You mean.
Was it South Atlantic?
Yeah, the South Atlantic. South Pacific, Southeastern Pacific doesn't have very many, and nor does the South Atlantic. The potential intensities are low there. That's the proximate reason. Why are they low? There's, I would say, a lot of divergence of ocean heat flux, particularly in the South Atlantic, and convergence in the North Atlantic. So the water is colder than it would be if it were in equilibrium, and that really depresses the potential intensity. The South Atlantic has had 2 tropical cyclones in the historical records, and I bet there are more if you wanted to go through ship's logs, but they're very rare there.
More crucial questions in here? Emerging? Last chance?
Can I go for my second one?
Let's go first over here, and then we'll go back.
I've got a question going back to the very beginning of what you said, where you're giving
Yeah.
sort of the background
Right.
on
Right.
climate change.
Yeah.
Water vapor. Water vapor is a greenhouse gas. Why don't you get warmer, you get more water vapor? Why doesn't it just spin out of control? You get more water vapor.
Yeah, that's a good question. It's a positive feedback. Every single study that's ever been done of it concludes that warmer atmosphere has more water vapor in it globally. The reason it doesn't spin out of control is that there's an even more powerful negative feedback. And the most powerful one being just the temperature itself. In other words, a hotter atmosphere emits more radiation to space than a colder atmosphere does. And that does stop it from going out of control. Having said that, there is a theoretical limit in temperature, because not only does the water vapor increase with temperature, but the rate at which it increases also goes up with temperature. So it becomes more and more powerful feedback effect. And at a critical temperature, it does run away. And it runs away theoretically until you've evaporated the entire ocean into the atmosphere. And that is sort of what we think might have happened on Venus, which is very hot, even though most people say Venus is hot because it's closer to the sun. Well, of course, it is closer to the sun, that we know, but it's actually a brighter planet. It reflects more of the sunlight than the Earth does. And if you look at the absorbed radiation on Venus, it's actually less than the Earth, remarkably, but it's got surface temperatures, I don't know, in hundreds and hundreds of degrees centigrade. And that's because it has so much carbon dioxide in the atmosphere.
So I shouldn't be particularly concerned about that on Earth.
No, I don't think you have to be concerned about that. We're not driving it that hard. I hope not. Yeah.
Excellent. Last question over there.
Well,
Transition.
The second question.
Can I get the second one?
Well, okay, so, storms take 3 to 4 to 5 days to develop. And the Atlantic Ocean is kind of a small ocean. And if they start developing, as some of them do off the coast of Africa, it's typically not until they reach the central Atlantic or even the Caribbean before they're declared to be hurricanes. If I remember your question correctly, that sort of explains why you see more tracks in the western part of the Atlantic than off of Africa. Yeah.
It's really why there and not somewhere else?
You mean further north, for example? Yeah, well, it's just where the potential intensities are high, and also where there are a lot of triggering disturbances in the easterly flow coming off of Africa. Yep.
So while transitioning to the last slide for the lecture, I have a question.
Yes.
You've been talking about high surface temperatures impacting the rates of and the magnitudes of storms. What is the effect of a stronger climate variability in time and space in the formation of the rate and the size of storms?
That's a good question. So in my brief summary of things, I really skipped over a lot of things that go into the formation of tropical cyclones, not just potential intensity or this inhibition, but there's wind shear, there's vorticity. And once the storms form, their tracks are governed by the general circulation of the atmosphere, including its variability. So one of the things that we have tried to do is to take that all into account. And what we discover when we do that is that we get robust results for the current climate. But if you try to downscale climate models, because they're so different from one another, the results are kind of all over the place. But nevertheless, if you look at landfalling storms, they can be easily affected more by changes in the tracks than by changes in either the location or rate at which they're formed. So it's perfectly possible that you'd have more storms formed in the Atlantic, but less damage in the US if in fact they systematically curve off into the ocean before they make landfall in the future climate. And that actually does happen in some models. So you have to really include all of that. It's a beef I have also with the National Weather Service that I tell them they shouldn't make seasonal hurricane forecasts because they're inadvertently deeply misleading. They're forecasting quantity almost nobody is interested in except Lloyd's insuring ships at sea, which is the number of hurricanes in the North Atlantic. It doesn't matter. Okay, it has very little to do with the rate of intense landfalling hurricanes. And yet everybody on the street interprets it that way. So Andrew, which at the time it occurred in 1992, was the most devastating hurricane in US history in terms of damage, occurred also in the quietest year, one of the quietest years we ever had. All right, it's anecdotal, but the statistics bear that out. You don't want to look at basin-wide activity if you're interested in the real McCoy, and that illustrates one aspect of how important variability is in this problem.
Interesting.
Yeah.
Let's thank the speaker.
Thanks.
Thank you.